So again, here we're just going to review through a few of these different circuit schematic representations. So like I've said previously, the schematic is kind of the final engineering drawing. So these indicate different parts on the schematic. So we've gone through all of these before. The only ones that might be slightly new are the diode in the bottom left-hand corner. And actually, in the very top right-hand corner, we have a connection point. So a connection point, or we also call them test points, are where we design points into our circuit board or into our circuit that we can test voltages at or currents at to be able to determine optimal function of that circuit to make sure it's working. So even in satellites, we always put, in satellite CCAs and circuit cards, we always put test points so that it's much easier to diagnose if there's a problem or if something happens during vibe testing or during thermal testing or thermal shock or whatnot. This allows us to have an easy, clean access instead of having to either go in or sometimes not even being able to test the circuit again. So there's something that you do in circuit boards where it's called conformal coating. It's like a thin plastic resin, kind of an epoxy that you coat on the top of them. And that kind of locks everything down into place, and that makes sure that if water gets in there, it doesn't touch the circuit and short circuit it, or dust, or something like tin whiskers if you're doing satellites. Tin has this property that it makes little whiskers that come out, and that can short things. So we usually will cover over that with something like conformal coating, so that just to make sure that nothing can get in there and give us a short circuit. However, whenever we do conformal coating, that also covers up these connection points. So sometimes we even leave this connection point open so that we can test it later on to make sure everything is working. But other than that, make sure you know all of these flashcards, however you want to do it, to make sure that you understand what the circuit schematic representation is for each of these components. So this is a good example of a schematic diagram. So the schematic diagram is the final deliverable that the electrical engineer provides the mechanical in the handoff period. And so schematic diagrams can look like this and get significantly more complex as they go. Each one of these schematic diagrams can essentially function for one small part of maybe a much larger system. So over here on the left, just looking at it, I see a detector head A7 with a designation. And then if you look up, I see an error input amplifier A1. Each one of these is essentially a smaller subsystem of that larger system. And so sometimes on these schematic diagrams we'll also have connectors, and it'll say connection pins that'll go off to another slide. And so some of these schematic diagrams for like satellites or whatnot can be hundreds of pages long, with being connected essentially with individual connectors or junctions in between them. So important things I want to pull out on here. This is actually a lot like an engineering drawing diagram. So the drawing diagrams we make for piece parts or assemblies, but specifically metal piece parts, have always the same thing. You have the drawing representation in the middle, you have the notes at the bottom left, you have some kind of legend on the right, and then you have the designators as well, reference designators. So an electrical diagram, on the bottom left, you'll see the notes sign. This is just going to say all values are expressed in ohms, are expressed in microfarads. Sometimes you get some other things with different terminals or some other different notes about different piece parts or whatnot. Usually on the diagram too, there's two ways of doing piece parts. So let's just say you're trying to buy a transistor, or let's say a transistor from a very specific company because it has very specific properties that you're looking at. Sometimes you'll write that on the circuit diagram as the name of the transistor, but more often you'll use a reference designator. So let's give another example. So up at the top in the input error amplifier, which has its own reference designator as A1, in that circuit, you can see right underneath there's a C3, an R6, an R10, and R13. And each one of those is the reference designator that is going to point to essentially a parts list later on. And somebody, usually a parts engineer, is going to match that parts list with the parts. So if we're looking at the R6 right there, it says R6, 56 kilo ohms from what I can see from here. My eyes aren't so good. But if you're looking at the 56 kilo ohms, we've not designated or we've not specified exactly which brand of resistor, or actually the wattage hasn't been specified either. So a parts engineer will go back through and kind of add some of that information in as we go. If you do look, we have the Q1, Q3, Q2, Q3 underneath that. Those transistors, those are a little more specified. 2N220, and anyway, that'll be a parts engineer that goes through. But you want to know what kind of parts you're using. On the top right hand side, we have a symbol legend, and these actually are very rarely included on most schematic diagrams. Most people know exactly what you're talking about because you're going to use essentially a common set of symbols. The only thing that we might put in the symbol legend is something that's very, very different. So if there's a part that we're not used to using, or if there is some kind of designation on there that remove this part during testing or whatnot. Sometimes it'll go in the notes, sometimes it'll go in the legend to be able to show what that part is. Now, underneath that we have the device legend, and this is going to give us the reference designators for different sub-circuits inside there, subsystems of those circuits. So as we already talked about, we had A1, which is the input error amplifier, and over there this just gives kind of a call out of what that is, so that it makes it a little easier to know what you're talking about. On big systems like satellites and spacecraft, we're going to split each one of those up into a separate drawing, and each one of those is going to essentially become its own sheet on the drawing usually. And that way it keeps it a little cleaner for engineers to come through and check that everything is going, because it's a lot easier to look at one small system and then check that and then check the inputs and outputs than look at a much larger complex system, although sometimes a larger drawing like this works as well. For a mechanical engineer, this drawing here is more like an assembly drawing because we have all these subsystems inside of it kind of coming together as this full assembly. And that's how I like to think of this kind of schematics. I think that's it for this one. All right, let's continue on. So here we have just a few more examples of schematic diagrams. In the top left, it's showing how to attach a voltmeter or an ammeter in to a simple circuit. Essentially, there's just resistors in there. It's a resistor-based circuit. You have two in series, and you have, two in parallel there. But in the top right, we have a 12-watt audio amplifier. So the things to note in this one is you can see that you have your audio in signal, and then on the outside, on the very right-hand side of that one, you have essentially a speaker as your output. So you're taking on the left side this input, this audio in, and it's going to go through an op-amp, which you can see with the triangle symbol there. There's a bunch of resistors, which the resistor is essentially going to change how much amplification you're going to get with that op-amp. And then in between there, you're going to have a capacitor in there that you can see C2 is the reference designator for this one. That's going to be for some interesting smoothing things and whatnot. We can talk about that more later. And then on the same of that, after that, you're going to have two transistors, Q1 and Q2. And then at the same time, if we look out, coming out of Q1, right before Q1 actually in the circuit, you have a resistor and there's an LED. So this circuit is also going to do some LED output as well as the sound output that it's going to have. So this kind of circuit we're going to be able to do by the end of this course and understand how it works, how to calculate it out, and if different things go wrong in it, how can we correct them to make the circuit sound more like we want. So on the bottom left, we have another circuit here, just another example of an input-based circuit. There's an op-amp in there as well as a bunch of resistors. I see transistor in there too. I see a diode in there, a capacitor, some variable resistors, which variable resistor again is a potentiometer. Yeah, there's a couple of interesting things. Another capacitor, electrolytic capacitor. Yeah, so I hope you can, as I'm talking about these, that you can kind of go through and find them yourself because it's important as well. On the bottom right hand, we have, again, another small legend showing some different symbols. I think we've had all of these before. The incandescent lamp is a different symbol than we've had before, and same with the fuse. And actually, there's a couple different ways to draw fuses. This is one way. I'll show you a couple later on. Rheostat, variable potentiometer. That's slightly different than what we've seen before, but it's the same idea. It's a resistor that you can change the value of resistance of. We have a cell, a battery. Yeah, we'll go through some of these more later, but this is just another example of a slightly more simplified schematic diagrams than the previous slide. All right, let's do a basic review of different concepts and units before we head on. So Current, as we talked about before, current unit is amperes or amps. How many amps of current do we have? And we denote it by I. I is just the symbol that we're going to use to represent it in all of our problems and in all of our solutions that we're going to work at. So what is current? What is an amp? An amp is a coulomb per second, a C over S. And remember, we had that in one of the previous examples when we were deriving current and the current versus charge graphs and how charge and current relate to each other. So that's probably the first one that we looked at, and that's going to be one of the most important. All of these are important, so you want to make sure you really have these down pat before we go on. Have these memorized, put them on flashcards, whatever you want, because there's no way to get to more advanced topics than understanding that an amp is a coulomb per second. So for resistance, again, we denote resistance by R, and it's measured in ohms. And remember, oftentimes we'll have some kind of prefix in there, kiloohm, megaohm. Those come up very often, so you got to remember the prefixes for these as well. Saying I have a 10,000 ohm resistor is a little awkward when we have prefixes that are specifically made for that. The unit of ohms, again, if you want to break it down, it's volts per amp. And that's the unit of ohms there. You see the little symbol as well. For voltage, what is voltage? Voltage is the electric potential. Again, that's kind of you can think of it as the force at which energy or joules are moving per coulomb. So we denote it by V. V equals joules over coulomb. Remember, joules is a unit of energy. Coulombs is essentially what we use for charge. So you're saying how much energy per charge, and that's going to be volt. That's kind of the pushing force of, if you think of the water analogy that we were talking about before. That's essentially the analogous to the pressure caused by the height change. That's what volts are. So the fundamental unit of electrical charge is coulomb. An electron has a charge of minus 1.6 times 10 to the minus 19th coulombs. That is an extremely small charge per electron. So that's another thing you've got to keep in mind as well, that 1 coulomb is a significantly large amount of electrons flowing through. I think that's it on this slide. If you have questions on this, I'm going to post a couple videos that you can go through to make sure that you're solid. Some of those videos I'll mark as optional and some I'll mark as not optional. If you feel like you want a little bit more depth in this, you can go the non-optional ones. You could do the optional ones and ignore the non-optional ones and do those. So here I just want to review through some of the basic equations that we've already had before we start introducing new ones. The first one is Ohm's law, V equals IR, or if you're looking a little more at time, voltage at a given time equals the current at a given time times the resistance, V equals IR. Voltage is in volts, equals I, which is current in amps, equals resistance, R, which is in ohms. And again, one of the main reasons we use this equation, if we look at the top right, is we're trying to look at the linear region. The equation, Ohm's law, V equals IR, is a linear equation. There's no exponents or anything in it. So we're looking at the range between the negative I max, or the negative current max, and the positive current max. And this is on a graph between current and voltage. What this is saying is that if we go beyond a rating on our resistor, beyond the current rating, the I max rating, that we can get some nonlinear behavior, and the nonlinear will not let our equations work out as nicely as they do right now. So V equals IR, we're going to presume for most of this class that we're talking about the linear region, especially when concerned with resistance or resistors. Another important part that you can do with this is I equals V over R, or R equals V over I. These are all the same equations that we can rearrange in different ways to solve for the other missing point. So if you're trying to find voltage, you put voltage equals current times resistance. That's the first one. That's the easiest. But you can move these around if you're trying to find different things in the circuit. So if you're trying to find how much a spot of resistance is, as long as you know the voltage and the current at that spot, you can back calculate what the resistance is. So these are very helpful to use in different ways in solving later things like Kirchhoff's voltage law and Kirchhoff's current law. Finally, we have the power equations. P equals VI. Power, which is in watts, equals V, which is in volts, times I, which is current, in amps. So volts times amps equals watts. And interesting there, you see also I squared R and V squared over R. So how do we get those? Well, we go back to Ohm's law and we can plug one in. So let's take that P equals VI. Let's substitute Ohm's law because we know voltage equals current times resistance. And let's put the IR in for that V. Then we're going to get P equals I times R times I, which is I squared R. Or we can also substitute in one of the current as well. So P equals V times V over R. And that's how you're going to get the V squared over R. So these equations kind of can be plugged into each other, essentially, to be able to solve for things that you're missing in the circuit. So got to be a little bit creative on that, of sometimes how you're going to get to the final solution that you want with what given information you have. So the next thing we're going to look at here, coming up in these next couple slides, are Kirchhoff's current law and Kirchhoff's voltage law. And you've had a brief introduction to these in physics, but I want to make sure that these are really nailed down because these are very important ways of solving electrical circuits. Kirchhoff's current law essentially states that the algebraic sum of the currents entering a node must always be zero. Kirchhoff's voltage law is the algebraic sum of the voltages around a closed loop must also always be equal to zero. So both of these are essentially two different forms of conservation that we're going to look at a little bit more in the next coming slides.